So we've seen all the pieces that we need to build this interpreter in theory. Now we actually want to take a look at the code that we need in order to make it run. So what exactly are we going to implement here? Well, what we're going to implement is the language that we saw described in the previous section, the syntax and semantics, but we're going to put in 2 additional pieces just to be a little bit more realistic, and because we're going to need them for later weeks in the course. First, we're going to implement negative numbers, which are pretty simple. You can put a unary minus in front of something, and that number is negative then, or that sub-expression is negative. And we're going to allow parentheses, so you can actually express any arithmetic expression with the 4 functions that we're talking about. So first we need to implement a data type for this abstract syntax tree, because the abstract syntax tree is the way the 2 pieces of the interpreter program are going to communicate. The parser is going to generate an abstract syntax tree, and then the interpreter or evaluation function is going to consume an abstract syntax tree. So in Haskell, we can use an algebraic data type. We have a calculator expression, which is either a number, which has an integer value, a negation sub-expression, which has a expression as its argument, a sum expression, which has 2 arguments, both of which are expressions, and the same for difference, product, and quotient. And we're going to say that this data type derives the show interface, so that when we're playing with this in the REPL, we can print it out and see what it is. And Haskell is able to generate the code so that it can show things automatically. So in order to actually parse the inputs for this parser, we're going to use a tool called Parsec, which is they call it a monadic parser combinator, but that's sort of getting into complicated Haskellese. The important thing is that it lets us write parsers by typing in things that look a lot like BNF. For example, we can type that a digit is one of a set of characters. A digit is either a character 0, or, this is what or looks like in the Parsec, like mini language, or a character 1, or a character 2, and we would go all the way up and say, or a character 9. Then we can say that a number consists of many digits, specifically 1 or more. And we have this many1 function that means 1 or more. This is like plus in a Perl-compatible regular expression, or having a digit and then another digit star in a standard regular expression. And then we can say, in order to actually use this parser, because number now is a description of a parser, we can call the parse function, which Parsec provides, pass it this parser that we've built, provide a string that it will return if it doesn't parse, and then the input string 1, 2, 3, 4. Alright, let's actually take a look at this Parsec thing in action. So here's the sample code for the assignment that I'll be giving for this week. And let's take a look at the parser that goes along with that. So this parser includes a rule called numExpr, which is a lot like the number rule I just showed you. A numExpr is 1 or more digits followed by some spaces, 0 or more spaces in this case. And as a value, so we save the digits in this variable num, and then we evaluate those as a integer value and return it. So this expression, this piece of the parser has a value equal to the numeric value of the number. Now let's take a look at that actually running. So to do that, I'll load up this Haskell interactive shell, GHCI, with this module. And then I will load up the Parsec module itself, so we can call the parse command that we want to call on these parsers that we've built. And as you can see, now we have both the parser module and the Parsec module available in our current scope in the shell. And so now we can call the parse function, on that num expr, pass it an error string, and give it 1, 2, 3, 4 as an input string. And it loads a bunch of packages. That's all implementation details of Parsec. And then it goes ahead and gives us this thing where it says write number 1, 2, 3, 4. Now, this is the parse tree that we expected. It's a number and it has the value 1, 2, 3, 4. And this write part is the way it tells us whether we got a answer that we wanted back, whether it successfully parsed or whether it did not successfully parse. Let's go ahead and pass it something that doesn't successfully parse. So in this case, it gives us back, instead of right, it says left. So this is telling us that this is a data type called either, which can have either the value right with a value or the value left with a value. And in this case, it's using right as success and left as error. And it passes back error string. And it also gives a detailed error about why the parse failed. Specifically, it got a star instead of the digit it expected. So that's how Parsec works. And it's doing exactly what we want, so we can go back to the slides. So here's that num expr from the file. And like I said, this num expr thing has this type, which I'm not going to explain except to say that this is the type that Parsec is expecting in its parsers. And then we say do, because this is in a monad, because we want to do something in a sequence. First, we want to match one or more digits. Then after that, we want to match some spaces, 0 or more spaces. And then we return this value, which is the integer value of the digits that we got, packaged up in this number thing, which is, if we go back a couple of slides, number is one of the possible data constructors for this calc expr data type, which is the abstract syntax tree data type. So this is building a leaf node in that abstract syntax tree. And then it returns it, which means that when we run the parser, this num and then the number value of the number it's parsing will be the value that the parser will spit out. So now that we can parse numbers, the next bit is that we need to be able to parse expressions. And this is a little bit more complicated. So first, the easy part is we have what we're calling a term expr for some reason. And that's either a number or an expr in parens. And that does what you'd expect if there's an expr in parens, it does the right thing, or it calls the number expr parser that we just saw. After that, we have this complicated piece where we build this thing called optable, and then called build expression parser on the optable. And what build expression parser does is it builds a expression parser that we can then call with the parsec parse command. And this correctly handles things like operator precedence. We want negation to be higher precedence than product or quotient. And we want product or quotient to be higher precedence than sum or difference. And build expression parser will just do all that for us. And so this magically does the right thing. And we can take a look at that if we want to. So down here, if we say, what was this thing called? It's actually called expr. So if we go ahead and parse expr, and then we're like 1 plus 2, it'll give us the number 1, the number 2, and then the sum of those guys, and then right, because this is not an error. If we do 1 plus 2 times 2, then we do the sum inside the product. And as you can see, the parens don't show up as any sort of element in the tree, because all they're doing is providing tree structure themselves. They don't show up as nodes in the tree. And that's basically the whole story. This thing is working as we would expect it to work. If I put in the letter K here, it'll still give us the error that we wanted. And that's the second session of this guy.